So basically, this national annexure gives the reduction. You have seen that, and so basically, when you have these flows uh, at the ground level, generally we expect the deformation of the building to be almost zero. So if you have all these piles of 20-meter length, and if you do not model the soil, then you cannot get the actual behavior of the building. The reason is that, these piles will become so unstable because they have a height of 20 meters without any restraint. And here also you have no restraint. Then you will find that, the structure is very unstable. So what you can do is, you can add these arbitrary links. And then another thing you can do is, you can say that assign the release, you can say it's pin-ended. So you can actually say that they are pin-ended connections. So the idea of these connections is just to make sure that the structure does not move horizontally. And with that, the structure will be stable enough to be analyzed. Otherwise, if you are not modeling the soil, the structure will be unstable. So that's the only reason why we have these links. And then another important thing is, when you look at the actual structure, there will be a ground slab. There will be a ground slab. So these pile caps cannot move on their own. So all these pile caps are connected each other. So with a ground slab. So if you model this building, it's again wrong. You have to actually model the ground slab as well. So I will open the next one. And that is 8. And in that one, you can see this one, you can see that I have connected the pile caps by using the ground slab. And here you can see I have defined a ground slab 200 millimeter thickness. And I have just connected these elements. These voids are not really there. I have to fill them up as well. I didn't do that because the whole idea of representing the ground slab is just to make sure that they are all connected. And here also I have to do this ground slab connection. Okay. Right. So then what I can do is get all these as pin-ended connections. And assign the releases, and then I can analyze. Now you can see there's some impact due to this foundation modeling also, because now the structure is taller and it's giving us different natural period of vibration value. But it's not a major problem because we know the normal structure is okay. But this gives a higher value because now we are having a taller structure. So the natural period of vibration is considered for the full structure, and it gives some flexibility because now the structure is taller. So now what we can do is we can actually see whether the structure is okay. Display view one of these planes where you can see all the piles, and we can see what the type of loads that will act on it: forces, stressors, shears. And we can look at the ultimate condition and the axial force, and you can see the values like 2749, and these are actually on the edge columns, so may not be the most heavily loaded. And if you look at a section through this one, that is y is 4.5 view, right, view here you can see the forces 3796, and this may be even higher, something like 4931. So that is the pile here. So that particular pile is supporting a concrete wall. So sometimes you might have to go for a slightly larger pile there. So those are the pile loads. And in addition to that, from a model like this, you can get the loads on shear walls as well. You can see the shear walls, and you can get loads acting on the shells. F22 is the stress in the vertical direction, and here you can see those stresses as well. So basically you can get all these axial forces, bending moments, and so on. And you can also see that in this one, display moment, and here you can see the type of moments that can occur in the piles. And so the moment transfer to the pile is fairly small. So we have considered full fixity, but still the moments are small. The reason is there are 4 piles. So the moment will be taken as an axial load by the piles. So it's okay. And then we'll also for one, and we have not applied any wind loads on the structure. So apply some wind loads. So we can look at one side view this one center. Oh, X is 20, yeah, 2 meters. So we get the wind loads acting on windward side and leeward side. And I will consider that the load here is 1 kilonewton per meter squared. So at each level you will get the width is 24 meters and the height is 3.6 meters. So 24 into 3.6 will give 86.4 kilonewtons at each floor level. And I will consider that leeward side coefficient is minus 0.5, windward side coefficient is 0.8. So last time example you saw those values are 0.8 and the leeward side can be the maximum is 0.5. So if I consider the load is 1 kilonewton per meter squared, in your case, if you want, you can actually calculate the actual value, but I'll take 1 kilonewton per meter squared. So last time we saw that, in the upper levels, the wind load will be in the range of 1 kilonewton per meter squared. If you look at the last week's example, the wind load is about 1 kilonewton per meter squared. So I'll take that value 1 into 24 into 3.6 will give 86.4 multiplied by 0.5. So you get 43.2. So I can say assign, select all these nodes and then assign join load forces wind in x direction, and I'll say in global x direction minus 43.2. Then you will ask, is it okay to apply? I think I have applied it in the wrong direction. Assign frame join loads forces, that is 43.2. Then you'll ask, whether it's okay to assign the wind loads like a point load. Like a point load. It's correct because, we have considered something like a rigid slab here. So because of that reason, if you apply the load in the line of action, then it will be okay because this is the line of action. And similarly, we have to apply the load here, and I'll apply arbitrary value, which is 1 into 24 into 3.6, that is 86.4 in multiplied by 0.8, 69.12 in the upper part, and for the lower part I'll allocate a slightly lower value because on the windward side the wind pressure is varying. So just to save time, I'll just apply some arbitrary values. Join load forces like 69.1, and for the lower ones I'll allocate something like 50. Sine join load forces 50. So you have to calculate, you can calculate the actual values and apply, but I'll just apply some arbitrary values. And similarly in the other direction also you can apply those values, and we'll very quickly apply some values. Y x is equal to 36. Uh, 50. and that is 3.6 into 30 into 0.5, 54 on this side. The sine win y 54 and this side 86.4 and I'll allocate some value like 70. Okay, so in both directions the wind loads are now acting. So you can see the wind loads that are acting on the structure. So so we save it and save as 2. So with all these loads, now we can see what's happening to the pi loads. Then I can ask view 20. And let's say what happens when the wind load is acting in x direction. Display show forces wind x. Then you can get some idea about what's happening. And here you can see. So here wind x, axial force is 220 and this pile is 102. So you can see now the axial load is taken by two behaviors. One is the cantilever behavior. That means all the wind is taken by the whole structure behaving as a cantilever. And here you can see this side piles are in compression, this side piles are in tension, right? So you can see the wind is now taken as a load acting on the full structure, and so it considers that the structure is behaving as a cantilever, and because it's a cantilever with a full moment acting on the whole structure, the columns, the piles in the windward side will go into tension, whereas piles in the leeward side will go into compression. So these piles are in compression, these piles are in tension. So that's the behavior you get due to the cantilever action. So basically the whole structure is behaving like a cantilever. So with that, you can see what happens to the loads service condition loads, axial loads, you can see they will not change very much because only these piles are subjected to tension and compression. Here the compression will increase. So that's how it behaves. And if you look at the forces due to wind load, look at the moment is still very small. So basically, although wind is a lateral load and it is causing a moment at the foundation level, it's a global effect, it's not a local effect. So that's why these piles are not carrying high bending moments. So the pile cap does not transfer much moment onto the pile. And so when you provide something like 0.8 to 1% reinforcement in the pile, it will be more than sufficient to take account of any bending moment transferred onto the pile. So that is one thing that I wanted to show you. And any question on this? I have just applied some arbitrary wind loads, reasonably representative, not very accurate, just to show you the overall behavior of the structure. Any question on this? Can you understand what I have explained? Any feedback, please?
Okay, it's okay.
Yeah. Now the next question is, can you represent the soil with springs? So for that, I'll open. So save this as UI3. Now I'm going to the next step. That is, representing all these as springs. So the first thing is, we'll go to this one, view, and I will remove all these elements. I deleted all those elements, and so now you have the structure, and we'll just analyze it. Sometimes it might crash, so let it be. It might become unstable, not 100% sure, but as it is, you can see it's not a very stable structure. Now you can see what has happened to the first mode of vibration, 7.31. So although it looks stable, it's fairly unstable because there's no restraint. So now I'm going to show you that this is not a workable model. So how do you convert it to a workable model? So the way that we can convert it to a workable model is by applying strings. Now the question is, how do you apply springs? And what do you mean by a spring? So when you want to have a spring, we can have the pile, and we can divide the pile into a certain interval. Let's say 1 meter interval, 1 meter interval. And so if you look at the pile, represent the soil, we can apply a spring this way, apply a spring this way. So when you apply a spring, the important property is spring constant, expressed as kilonewtons per meter. So basically, to have 1 meter deformation, how much load that you have to apply here? To create a 1 meter deformation, how much load that you have to apply here? So that's how you look at the spring constant. So we can have two types of soils. One is sandy soil, the other one is clay soil. And in our conditions, we have laterite soil, which is a mix of clay, sand, and gravel. So first we'll see how we deal with sandy soils and the clay soils. So in the case of clay soils, if the soil is of it's clay, that means you don't get any much friction. So what you get is only the cohesion, C, U, the cohesion, undrained cohesion. So if the soil is over consolidated, that means the clay soil has been there for a long period of time, and during this period, various extra loads have come on this due to flooding or due to ice age or whatever the reason. The soil is over consolidated. Then the spring constant value does not vary with the height. It's a constant value, and it depends on the soil strength. Depends on the soil strength. Whereas in the case of sandy soils, the spring constant increases with the depth. The spring constant increases, but generally you will have a maximum value for this. You will have a maximum value for this, and so the spring constant will increase, but you will generally go for a maximum value for the spring constant. So then you can also have rock. In rock also, the variation will be something like this. But we have to now find suitable values for all these. And then when you have laterite soil, if the laterite soil is more of sandy nature, then you can consider it as sand. And if the laterite soil contains a lot of clay, then you can even consider it as a clay soil as well. So depending on the soil type, we have to decide a suitable value for these spring constants. So the question is, how to find these values? Now to find these values, share this note. So we can say modulus of subgate reaction in horizontal direction. And first thing is, you know, you have to identify the type of soil. And the soil can be, if the SPT value in the field is less than 2, it's a very soft soil, something like peaty soils and so on. And if the SPT value is 2 to 4, it's a very soft soil. And if the SPT value in the clay soil is 4 to 8, it's a firm soil, but not very strong. But it's not a very weak soil. It is a firm soil, having a bearing capacity of something like 40 to 50 kilonewtons per meter squared. And if it is between 8 to 15, it's a stiff clay. And if it is between 15 to 30, it's a very stiff clay. Or if it is more than 30, it's a hard clay. So you know that, you know, these values are actually, these SPT values are affected by the water table. So depending on the height of the water table, these values can vary, but the fact that water table is present is already taken into account. So on the basis of SPT value, you can determine the undrained cohesion for these clay soils. Using this equation, undrained cohesion is equal to 4.5 times the SPT value. And that actually comes with this particular experiment. And there you can see when the plasticity index of the soil is in this region, which is a very weak soil, or when the plasticity index is in this region, when it's a stronger soil, you know, a value like 4.5 is a very reasonable figure to relate the undrained cohesion with the SPT value. So based on that, this particular chart, function F1 is FCU divided by N60. So basically, this shows that, you know, value like 4.5 may be a very reasonable value. So Cu is equal to 4.5 times N. Some engineers simply say Cu is equal to 5 times N. So based on that, you can calculate the FCU value. And then there's a relationship between the elastic modulus of soil and Cu value. So elastic modulus of soil and Cu value, depending on the plasticity index and the over-consolidation ratio, you can determine different values. And if it is a soil, let's say you have a soil with the fill, a recent fill of 1 or 2 meters, which means the soil underneath that fill wouldn't have been subjected to much consolidation. Then you can say the over-consolidation ratio is low. Otherwise, you know, better to consider that the over-consolidation ratio is between 3 to 5. And if you have any doubt, you can even go for value like 5. So more than 5. So you can be in this range or this range. And depending on the type of soil, say when you have a laterite soil, plasticity index will be less than 30. And if you have very weak clay soil, the plasticity index can be between 30 to 50, but it's very unlikely to be more than 50. So Plastic index more than 50 is, very weak soil. So based on that, you can actually select a suitable value to be used for this ratio, depending on the SPT value. So if the SPT value is about 2, you might be in this range. If the SPT value is about 8, you might use this particular relationship. And if the SPT value is about 15, you might use this relationship. Because when the SPT value is high, the plasticity index will be lower. So based on that, you can actually select some values. Depending on the bow log, you have to come up with some reasonable values. And then when you know the elastic modulus, the horizontal subgrade reaction is given by this particular equation, and elastic modulus will be in kilonewtons per meter squared, because FCU is in kilonewtons per meter squared. So this is in kilonewtons per meter squared, and you have to divide it with the width of the pile. Then you get the answer in kilonewtons per meter cube. And then to find the spring constant, you have to multiply the horizontal modulus of subgrade reaction Ks by the area represented by the spring. So the area represented by the spring is the width of the pile multiplied by the spacing of the springs. So if you are going to have a spring every 1 meter, then Ks will be B ES over B IW 1 minus nu squared multiplied by B times 1 meter. Then you will find Ks is equal to ES. The reason is this IW, the influencing factor, is taken as 1, and the value of nu is 0.3, and 0.3 squared is 0.09, 1 minus 0.09 is 0.9. So because of this reason, we generally say Ks is equal to ES over B, and then the spring constant will be ES multiplied by B, ES over B multiplied by B times, B is the width of the pile, multiplied by the spacing of the springs, which is, if you are having springs every 1 meter, then Ksc will be equal to ES. So this way you can actually work out the spring constant for clay soils. So next time I'll show you with an example, and then we'll apply those values. And similarly, you can also find the modulus of subgrade reaction for sandy soils, depending on the SPT value again. And based on that, you can work out the friction angle and the relative density. And then there's a chart to find the value of the spring constant can be found, NH value can be found. This NH value can be found from the chart, and based on that you can work out the spring constant for the piles. So this way you can actually work out the spring constant for clay soils and sandy soils. So I will load this onto Moodle today, but next day I will explain you how this can be used, and the springs can be applied, and the results can be interpreted. Okay. So today I have just briefly showed you, so I'll upload this, just go through the note, and then for the rock also there's another explanation. For the rock, it depends on the kind of fractures in the rock. So if you have a lot of fractures in the rock, then we know the rock quality designation, or RQD, will be a low value. So if RQD is a low value, like here, then this factor will be very small, and EM is the EM is the elastic modulus of the rock mass without any fractures. So if you have a rock, you have to estimate the elastic modulus. And one good indication that you can have is which is stronger, rock or concrete? Which is stronger, rock or concrete? What is the answer? Anybody? What do you think? Which is stronger, rock or concrete? Can somebody give some feedback? You are listening?
It can vary with the strength of concrete.
Yeah, but now concrete is a mix of cement and water and all that is there. So basically,
The most strength.
the rock will be much stronger. So you know the elastic modulus of grade 30 concrete is about 30 kilonewtons per millimeter squared, right? 30 kilonewtons per millimeter squared. Oh, so basically, if you take unfractured rock, the elastic modulus can be easily in the range of 40 to 60 kilonewtons per millimeter squared. So it's stronger than concrete, right? So when you look at that, then you will find that the elastic modulus of rock, can be something like 40 into 10 to the power 6 kilonewtons per meter squared. So then if the RQD value is something like say 50, then you get 0.1, right? If it is like 50, you get 0.1. So you have to multiply the elastic modulus of the intact rock mass by 0.1. Then you will end up with something like 4 into 10 to the power 6 kilonewtons per meter squared as the E value for the rock mass, the fractured rock. Whereas if it is highly fractured, like RQD is only 10, then it can be only about 0.1 times, 0.01 times the elastic modulus. Then it can drop to about 0.4 into 10 to the power 6. Then it will be only about 400,000 kilonewtons per meter squared. So the rock, the values that you get for rock is much higher than the values that you get for soil, clay and sandy soils. And generally for clay and sandy soils, you might be in the range of 2,000 to 50,000, 40,000. Sometimes it can go up to about 100,000 as well. But in rock, the horizontal reaction can be much higher. So basically, that's why, you know, when you anchor the pile into the rock, it becomes almost fixed. So that's what you can gather from this. So we'll discuss this in little more detail next time. And also we'll apply the soil springs to this model and see how it behaves. Is it okay? Any questions that you like to ask? Any questions? And can you do a model in one of the selected software? It can be SAP 2000 or Midas. What is the software that you prefer to use? What is the software that you prefer to use? Some feedback, please.
SAP 2000.
Yeah, you can use either SAP 2000 or Midas. Midas, you have access, is that right?
Yes, sir.
It's working, right?
Yeah.
Okay. So all of you can use Midas as well. So if you want, you can use Midas and do the modeling, because you have, then you can, here I have shown you a model in SAP. Then you have a different model in Midas, right? Okay. So you have to do an assignment on these. So I'll post that assignment also shortly, right? So any questions, you can ask next time. And next time I'll show you how to model the building with the foundation and the springs. Okay, with that, shall I end the lecture here? If you don't have any other questions. Any questions you would like to ask, or shall I end the lecture? Is it okay?
Okay, sir.
Huh?
No questions.
No questions. Okay.
Yes, sir.